Hello, everybody. I'm Dr. Indranil Ghoshra. I'm a lecturer or equivalently assistant professor in Queen's University, Belfast. And in this talk, I'll talk about one protocol design, which is on the PEKS. PEKS is the public key encryption scheme with search. So in this protocol, there are three players. One is the data owner, one is the cloud server or the server, and one is the user. So what happens is the following: data owner has its data. Data owner will encrypt the data and upload it in the cloud. For the security of the data, he will encrypt the data. But with the traditional encryption, if you upload the data encrypted, then you lose the usability of the data, in a sense that you cannot search on a data. So it is a searchable encryption where data owner can delegate the facility of searching over the data to the third party. And this third party is the user. So the first such PEK scheme was proposed in Eurocrypt 2004 by Dan Bonnet and his team. The main problem with the scheme is that it suffers from the linkability problem. I'll come to this. And to overcome that problem, a paper was published in Elsevier 2017. And the scheme was called PSEKS, and they achieved partial unlinkability so as to improve the security partially a little bit. And what we achieved in this paper is a full unlinkability in terms of the user key indistinguishability and server key indistinguishability. I'll come to all those definitions. So the major contribution is the introduction of these two concepts, UKI and SKI security. And we provide the formal proof followed by the definition. And finally, we implement as a proof of concept our scheme, and we validate it against one timid data, which is a academic data set. So now let me explain all those security one by one. So in the P case of the Bonnet, the scheme of Bonnet, what happens is the following: the public key encryption scheme means the encryption key is a public key. So the encryption facility is available to the rest of the world. Anybody and everybody can come and get their data encrypted. So the problem with that facility is the following. Let's say I'm the data owner. I'm uploading my data by encrypting my data using my key in a third-party cloud. And an adversary can also come and get adversarial data encrypted with my public key, which is a public key. That's why he can access. So encryption is a publicly available facility. So anybody can get that data encrypted and upload in the same cloud. The problem is the following. In the future, whosoever will be searching using a secure trapdoor mechanism, the same search will propagate over the adversarial data. And if there is a match in the adversarial data, adversary can guess the search pattern. So that is called the UKI security, where the secrecy of the user's search is getting revealed to the adversary. And quite similar to that is SKI security, where the same piece of data from the same data, same data owner, if it is getting saved in two different servers, the search pattern using the two different servers can be linked so as to reveal whether two servers are saving the data from the same source or not. That is the server key indistinguishability. So now I'll very precisely talk about the construction of the scheme. So first, the setup. This takes lambda as the security parameter, which is in our case was a parameter of the length of 1024 bit, and it will deliver the following components: two group elements, G and G1, P is the prime number, small g being the generator of the group, and E is the bilinear pairing, and H is the mapping, which maps any text to the group element. Now, when it comes to the key generation, the main thing that we did, unlike the previous schemes, is that we identified these three players in the game. One is user, one is cloud, and one is the data owner. Cloud means the server. And for the user, that is the third party who are going to search, we generated a pair of keys, secret key and the public key, which is coming in the color brown, SKR and PKR. And when it comes to the cloud, that is the cloud server. Cloud server is also having two keys. One is SKC, one is PKC, which is coming with the color of a cyan. And when it comes to the data owner, that is the one who owns the data, who will encrypt and upload the data. We have three keys. One is the public key, which is the PKS. One is the secret key, which is SKS. And one is a special key, which is made for to facilitate the search, which is the trapdoor key, which is PKT. And if you take a look of, if you take a closer look of these constructs, you will see that this secret key is nothing but a random number, small b, and the public key PKS is G power B. So the secrecy, I mean, the main power of the security is coming from the Diffie-Hellman property of the group, where if I give you G power B and G is known to you, you cannot find out the log of that element, which is the B. And the fourth point is very crucial, which is the sweetest part of the entire scheme. So now, if you take a look at this PKT, PKT is nothing but the PKC to the power SKS. Now, which gives you the simple expression of G power BC. Now, if you compute the SKCth root of PKT, so you get rid of this C part. So PKT raised to the power 1 by SKC is going to give you this G power B. This simple mathematical expression can be leveraged when it comes to the actual computation. We'll come to that. Now, when it comes to the trapdoor generation, what is trapdoor? Trapdoor is you have your encrypted data in the cloud, and when it comes to the search of the data, your search needs to be protected because your search reveals your intent. So you don't go and search directly with your plain text search query. Search query needs to be protected. You convert your search query into the trapdoor. So who is searching? Searching is done by the user whose keys are coming in brown. And where he is searching in a cloud. That public key of that cloud is coming in the cyan. And what he's searching a data encrypted by the data owner, and the keys of those owners are coming in red. So after having these parameters, what trapdoor generation mechanism delivers is a two-component output, A and B, where A is, as you see in the screen, this component, and B is the second component. This seemingly complex looking component will be having very nice property of what is that called, a bilinear pairing. This pairing is famously denoted by this small e. So this expression will get a very specific form when we'll show you as to how this trapdoor and the search works. So this is the trapdoor. So what happens is, whosoever will be searching for a particular word, which is W, First, he will convert this W to a group element. He will raise this element to the power skr, where skr is the secret key of that fellow who is searching. This R is a random group element which randomly, uniformly at random, he will gather from the group. This is the public key of the data owner, which is a public information which he can take at any point of time. So he can compute the first component. The only secret part is this, which is his own secret. So he knows his secret. And the second component is this, where this PKT is a particular key which is formed by the data owner. So if I go one slide back, so this PKT is generated by the data owner. So it is meant for public access, and whosoever will be searching will be requesting the data owner, and data owner can give it. So now the user has this key, and the randomness, whatever he generated, he will plug that to compute the second component. Now, these two components together is the trapdoor. Now, when it comes to the encryption, what will happen is that encryption is done by the data owner. So all he has is a data, which is the word W, and his key. One is the secret key and one is the public key. So when it comes to the encryption again generates two components, C1 and C2. C1 is this. He will convert the word, the data, into a group element by this hashing, and the element he will raise to the power of the secret key multiplied by G. The small g is the generator of the group, which is publicly available, raised to the power some random R. And the second component is the public key raised to the power the same random, which is R. And for the encryption of that word W, he will set the encryption of the word W as C, which is C1 and C2, these two components. And he will redirect this encrypted text, the ciphertext, to the server. Now, at certain point in the future, imagine that in the server there are encryptions of several texts which is of the form C1 and C2. So there are many blocks of C1, C2, C1, C2, and so on. And one user is trying to search against a particular word. So first thing that user will do is to compute this TW. The computation is just explained. The user needs the public key of the data owner, which is PKS, the public key of his own, which is the PKR, and also the secret key of the cloud server. So this key comes with a permission. So when whosoever is trying to search will give his search query to the server. If he is a registered member, then SKC will come in place. And server has the ciphertext. And the trapdoor is available from the search query, because the search query is the trapdoor. It is not the plain text, it is the trapdoor. So the first thing will be to parse the ciphertext into these two components, C1 and C2, and to parse the trapdoor into A and B. The public keys, will be will be gathered from the system, because these are the public informations which are freely available in the system. And the secret key, as I've said, that will be in place provided the user is a registered user of that cloud. And what the cloud algorithm will do is simple. Cloud algorithm will check this equality. Cloud algorithm will simply check whether the left-hand side of this expression is same as the right-hand side. If yes, then it will say that there's a match, search is positive, otherwise it will say 0. Now let us take a look as to how this works. So see, the ciphertext has two components, C1, C2, where C1 and C2 is, as we computed earlier, I just plugged those values over here. And TW, the trapdoor, has also two components, A and B, where A and B I just copied from the previous slide over here. So these are the expressions for A and B. Now, if you remember this, I will start by taking the left-hand side of this expression. So if I compute this left-hand side, now I will replace this A, B, and C2 by from the top two lines. So it will be something like this. Now, if we take a closer look at this PKT, by the property of this bilinear pairing, PKT, the component which is this one, this component is same as PKT raised to the power 1 by SKC. Now allow me to go a couple of slides back, and as I have said that the most sweetest part is this one. So PKT raised to the power SKC, the simple looking expression. So you are dealing with your trapdoor key raised to the power 1 upon the cloud secret key is going to give you PKS, which is the server's public key. Sorry, the data owner's public key, because this PKS is the data owner's key. This simple yet very subtle transformation is what is utilized over here. Now, this transformation is going to give you the rest of the computation, though complicated but doable, is just that if you simply at this line, if you replace this by PKS, then the rest of the computation is easy, and eventually you end up showing that these two components are equal, provided the intended word is the same word. Otherwise, it will not match. Now, the novelty, if I say, is in two folds. One is the SKI, and one is the UKI. So SKI, the server key indistinguishability, means that so the game here is going to give you is trying to simulate the same situation where there is one user whose key is the first line, and there are two clouds. There are two clouds, which is one cloud is denoted by the C0 and another cloud is by C1, and these are generated, and also the rest of the keys are also generated accordingly. And now at certain point, if in the game, out of those two servers, one is chosen at random by this unbiased coin, and according to the selection of the coin, I picked one of those servers, meaning from these two I have selected one of the servers. Now after this selection, if I give it to the adversary, adversarial access to the trapdoor and the hash function is still there. They have the oracle access of these two. But despite that, adversary will not be in a position to distinguish and correctly tell whether this D is actually picked 0 or 1. So the advantage of this probability is negligible. So that is the formal definition of SKI. The story that I just mentioned, when put formally, looks like this. And something similar is UKI. In the UKI, what we are doing is, if you take a look, I marked it red. So here there are two users. I mean, we have selected two users. We are playing the game by generating two users and one fixed cloud. In the last example, there were two clouds and one fixed user, but here there are two users and one fixed cloud. And in the seemingly complicated looking game structure, the same coin is flipped, unbiased coin, and out of those two I mean, users, one is selected uniformly at random, and the trapdoor is given. And with the facility of Oracle access of the trapdoor and the hash function, and the adversary is not in a position to distinguish and pinpoint as to which of those two servers, two users was given. That is to say that the advantage of this game is negligible. So that is the definition of EQI. We provided the full proof in the paper. And when it comes to the implementation, the major contribution is not in the implementation, because so far we don't see any other scheme with which we can compare in terms of the timing performance. But the work is not yet finished. We have a minimum viable product out of it, and we are trying to integrate and apply this for biggest animal biobank data in Northern Ireland, in UK. But so far we applied that on a timid data set, and this is the performance graph roughly. So thank you for your attention, and I'm ready to accept questions if there is any.